Okay, so first, if you have your RStudio, you can use RStudio, right? So we are going to use a few libraries. Okay, so first we prepare environment. Okay, always start with make sure the environment is your computer environment or your desktop environment is now ready for the analysis. So we can load library Heaven. Library Heaven, Heaven package is a package that can read SPSS, Strata, and SAS data into R. Okay, that's library Heaven. One other library that you can use is Foreign. However, Foreign cannot read Stata file beyond version 12. Okay, so that's a problem with Foreign. So that's why I prefer to use Heaven package. Okay, Heaven package. Selamat datang Syarul. Okay, tak apa, dia dengar tu.
Ya, terima kasih Prof. Terima kasih.
Okay, right. And then after that we load package Survivor. Survivor is the package that we can run survival analysis. It is one of the most used survival package lah. Okay, one of the most used survival package in R. But there are other packages that we can use for survival analysis. But I think Survivor is good enough. And one other package is GG45. GG45 is a package that can produce a handsome one-line survival plots. Okay, this is what written lah in the package. Okay, you can easily draw survival plots after we run survival analysis. So Heaven, Tidyverse for data wrangling and plotting, survival package to run survival analysis, GG45 to plot survival plots after survival analysis. Surv-Miner is another package we can use to plot survival analysis results or model. We learned this last semester. Summary tools, I like summary tools. Summary tools is a package that can quickly give a nice result from exploratory data analysis. Okay, summary tools. Some people prefer to use PSYCH package, but I think I prefer summary tools. Okay. And so once we got that packages loaded, then let's read data. This data comes with a survival package. Okay, so we don't have to read data. Even though I said here I load library Heaven, but I'm not going to use this. Okay, I'm not going to use this because I'm not going to read any SPSS data or SAS data. The data is already available in the package. So once we load the library, we load survival package, then the data is already there. We just simply by typing it, then we can call the data to R. Okay, but if you have data in SPSS, in Stata, or in SAS, then we have to use read underscore Stata or read underscore SPSS or read underscore SAS to call data from that format into R. Okay. So we just type veteran. Okay, we just type veteran. In this data there is 137 rows. So 137 observations. We have treatment 1 and I think 1 and 2. 1 and 2. Not sure. I think 1 and 2. 1 and 2. And then we have cell type. I use Glimpse. Glimpse can quickly give you the types and the formats of each of the variables. So I like to use Glimpse. So I can see that there are 137 rows and there are 8 variables. 1, 2, 3, 4, 5, 6, 7, 8. So we have treatment as double, 1 and 2. We have cell type as a factor variable, squamous, 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 and maybe I'm not sure what other types. And then we have time. This is time taken from the start of treatment and the outcome or the event of interest. Okay, the time taken until the development of the event or sensor. Okay, so we have status, and 1 and 0. I think 1 is the event of interest and 0 is sensor. Okay, you could 0 as sensor and 1 as the event of interest. Okay, but you can always change this to factor kan. Okay, however, in this data set, it's taken as a double variable. We have also Carnot type. I think Carnot type, diagnosis time, age, and prior. Okay. So if you want to know more about this data set, you can just maybe I'll just open my RC. Okay. Kena alih sikit, takut keluar soalan exam. Okay. Right, so we close everything, close all. Okay, so library, survival, and then okay, and then veteran. So because we want to know what veteran, what we have, what information we have for the veteran data, we just put as question mark there. Right, so we can see here it says that randomized trial, okay, randomized trial of 2 treatment regimes for lung cancer. Okay, so this is a standard survival analysis data set. So treatment is 1 and 2. 1 is standard, 2 is test. Cell type, 1 is squamous, 2 small cell, 3 adeno-CA, 4 large type lung cancer. Time is the survival time. Status, censoring status. Karnofsky, not Carnot type. Karnofsky performance score, 0 is 100 is good. Diagnosis time is months from diagnosis to randomization. Age in years. Prior is prior therapy, no. And 1 and 10 is yes. Oh, 10 is yes and not 1 yes. Okay, tak apa. Right. We can use this script -cr. Okay, -cr. This is from summary tools package, so it gives you a nice summary statistics for all the numerical variables. Okay, so the mean, standard deviation, mean, median, 25 percentile, 75 percentile, skewness, so on and so forth. It also gives you percent of valid, age, diagnosis time, Karnofsky score, prior treatment status, and whatnot. We know that prior is not a numerical variable. It's not a numerical variable. Cumanya this is coded as numerical variable. Status also is not actually a numerical variable, because status is censoring. 0 is censor, 1 is I think death. 1 is death. And then we can use FRAC. FRAC is the summary statistic for categorical data. So it says here that you ignore time, diagnosis time, and age. So it returns the frequency for treatment 1 and 2. So we have 69 on treatment 1 and 68 for treatment 2. Treatment 2 is the new treatment test. Okay, treatment 2 is the new treatment. No missing data. Cell type we have squamous, small cell, adeno, and large. There is no missing data. And then this is the status of the follow-up, whether 1 died and 0 is sensor. Okay, 1 died and 0 is sensor. Okay, we'll see again. 1 died, or it doesn't tell us. Okay, censoring status. Okay, and then Karnofsky score. Okay, Karnofsky score. Unfortunately or fortunately, I'm not sure why Karnofsky score is considered as, is also taken as a categorical data, ya kan? But actually it is not a categorical data, right? It is a numerical data. Okay, tapi tak apalah, no problem. And then prior treatment 0 and 10. 0 is no prior treatment, 10 is yes, have prior treatment. So first we run the non-parametric survival. Okay, the non-parametric survival, the most classic one, which is the Kaplan-Meier survival estimator. Okay, Kaplan-Meier estimator, Kaplan-Meier survival analysis, or Kaplan-Meier estimator. It is a non-parametric survival analysis. Okay, we use the function serve fit, and then we have serve, and then the time variable and the status variable. Okay, if you look here, serve fit, okay. Wait, serve surv, okay, surv. If you look here, notepad. So if you look here, this serve function, okay, the serve function, the serve function is important here because we want to tell that this is a survival data. Okay, survival data. If not, it will not work. Okay, we have to declare to R that this is a survival data, and in fact every software will have to do this. Okay, you have to, when you deal with survival data, you have to tell the software that this is a survival data. It has two components. Okay, it has two components, which is the time to and event. In this case, we have to, at least we have to have time and we have to have event. So the variable time here is the same with the variable time here. Okay, if this variable is written as duration, then you have to put duration here. Okay, you have to put duration here, and the event here, the event here refers to status here. Okay, refers to status here. If this is written as outcome, then you have to replace event with outcome. Okay, so be careful, don't write time and event. This time it says that what we are doing now, when we write the function, is it asks you, okay, where is the variable time? That's what it wants to know from us. And what is the variable for event? So we have to tell R that the variable time is the time itself, and the variable event is the variable name status. Okay, don't put event here because there is no variable event in our data set. Okay, don't forget. Okay, always a mistake there. If it is if the status is written as outcome, if let's say there is not status but outcome here, outcome, then you must write here as outcome. Okay, but again there are other ways of writing this. If you can refer back to our discussion last semester for Cox proportional hazard data for survival analysis, and there are other ways of writing this. Okay, first what I'm going to do is just to perform the overall Kaplan-Meier survival analysis. So we put serve fit and then type serve and then tell R that okay, variable time is time and variable event is status. And then we put tilde 1 and then tell R that the data set we are going to use is data set named veteran. Okay, then we run the function summary, and we'll get this. Okay, at time 1, what is the number of people at risk? 137. How many got the event? 2. And what is the survival probability? It's 0.985. 135. So now let's so 195 137, so 2 died, so it becomes 135, right? So 135 divided 137, so we get 1.9854, 0.985. Okay, that's how we do it. Okay, so this is so 1 die at time 2, so 134 divided by 135. Here at time 3, 1 died, so 133 divided by 134, and so on and so forth. Okay, is it? No, I don't think so. No, that's different. Yes, sila.
Time 1, time 2 ni macam mana kita nak tahu dia by year ke day ke dia dimension dekat atas?
Tak ada. Dalam data ni tak ada. So it depends on you lah. You so in this case I'm also tak sure apa ni, adakah dia bulan ke hari ke. So there is no way of knowing that. So kita kena tanya dia lah. Tapi but sometimes we have data yang apa ni that comes with date. For example, dia instead of time ni kan, dia tak ada time, but it has date of diagnosis and date of outcome, for example, right? And then for that example, which is more complicated, we can use lubridate. Ingat tak lubridate package? So we can minus the two date and then dapatkan in weeks, in days, in month. So use lubridate package to get the intervals, and from the intervals you can convert to days or weeks or months or years, whatever metrics that you need lah. Okay, in this case it's easy for us because time is already given to us, but most data is not that kind lah. You have to manually minus 2 days. Okay, minus the 2 days. So to do that, use a package lubridate, very useful. Okay, lubridate can also convert to epic weeks. Okay, epic weeks. And this 0.978, it is not 134 divided by 135. That's my mistake. It is not like that. Okay, it is not like that. Not 134 divide 135, which is 99. Okay, it is not. Okay, this is I've forgotten the formula already. I think this is this one, and then you 0.95. Okay, this one, take this one, Control C, then times this one, Control C, oops, Control V, masih silap lah, Control C, Control V, 0.978, okay, 0.978, which is this one, right? And then this one is this one times 133 divided by 134. So that's how you calculate the cumulative survival probability. So that's why it starts from 0.985 and it goes down and down and down and down until time 999, almost 1,000. Not sure 1,000 days ke 1,000 months ke, okay, not sure, where everybody dies and it reach zero survival probability. So this is the function autoplot. Okay, autoplot from the GG45 package. So you can plot the survival probability. So it starts from 100%, everybody survive, and after that it goes down, and every time you see this small square, no, small plus point, it means that this is where someone sensor, okay, someone sensor lost from the study, okay, 1 2 3 something, how many sensor, forgot the a few, 9, okay, I think 9 people sensor, goes down, okay. So you know that over time survival probability decreases, okay, and at 50% of survival, where 50% of patients died, the time is about somewhere here, right, somewhere here, okay. We if you refer to my previous note, we can calculate, or we can, you know, get the value of time here, okay, for survival probability equal 50%. This is okay. Now let's say we want to see the survival, we want to estimate the survival time or survival probability. We're not estimating time here, okay, we're not estimating time. We can estimate time only from parametric survival analysis, not from non-parametric, not from semi-parametric, okay. We can estimate the survival time using parametric survival analysis, okay, but we are estimating the survival probability for the non and the semi-parametric survival analysis. So again, we use the function serve fit and serve time and status. Remember, time is the variable time for your data, and status is the outcome or the event of the variable event for this data set. Then tilde treatment, and we want to compare if survival probability or survival estimate between two treatments is different or not. So and then we run the auto plot for this Kaplan-Meier estimates. So we can see this plot, right? So it shows that for both treatment, survival probability decreases over time. However, in treatment 2, it seems that they have a bit more favorable survival probability, okay, a bit more better survival probability in treatment 2, which is the new treatment, kan. However, we're not sure, right? We're not sure whether they, you know, if we look at the p-value, whether they are significantly different or not. We're not sure. So we want to check the p-value. So instead of doing auto plot, we can use GG surf plot from the Surf-Miner package. So we put the model from Kaplan-Meier, this one, and put it here. And then we, if we want to show the risk table, we can you know, choose the argument true for risk table, and if we don't want to see the confidence interval, put false here, and if we want to see the p-value, put p-value equal true, and yes, true to our you know, our observation is that even though there seems to be a little bit of better survival probability in treatment 2. It doesn't seem to be a lot of different lah. Okay, a lot of different. It doesn't show that, and p-value support our observations, where it says that the p-value for the survival probability difference in treatment 1 and treatment 2 is at 0.93. So it is bigger than 0.05. So we can say that there is no significant difference in the survival probability between treatment 1 and treatment 2, okay, over time. Don't say the difference in survival time, because we are not comparing survival time, okay. But if you use a parametric survival model, then you can say that, okay. But for Kaplan-Meier and Cox proportional hazard, we say that the survival probability between the two treatment is no different, okay. There is no difference in the survival probability between treatment 1 and treatment 2. Now we go to the more advanced model, which is the Cox proportional hazard regression. And I think maybe I suggest for you to do is you can add something here, okay. Maybe treatment plus categorical variable. Kaplan-Meier don't do well with numerical data, okay. So maybe you can add prior, okay. We can add prior. Maybe I can do this, okay. Let's do this. So we add treatment plus prior. Right, so we got that, and then we type, maybe too small for you, so I'm gonna besar sikit. Okay, treatment prior, and then treatment plus status of prior treatment, and then type summary, and then put this model inside. So it will show the survival probability for treatment 1 prior 0, and treatment 1 prior 10, treatment 2 prior 0, and treatment 2 prior 10. So you see, four survival probability or survival estimate. Can we plot this? Of course we can. So we just take this one, and or maybe we use auto plot first. We can use auto plot. For that I need to load library GG45. Okay, right. Okay, so auto plot. Alamak. Okay, not this one. Control V and see what happened. Auto plot KM treatment fit. Factor 3 is duplicate. Okay, it looks like auto plot doesn't work well with two covariates here. Okay, so let's try using ggsurf. Okay, ggsurf. Okay, so I need to load this one first. Library ggsurf, not ggsurf, surf minor. Okay, Right. Okay, now you can see this. So you see treatment 1 prior 0, treatment 1 prior 10. So and this is the p-value comparing the 4 groups. Okay, comparing the 4 groups. So yeah, it looks okay. It looks okay, right? So, but you know, the more groups you have, the more messy the plots will be lah. So that's one disadvantage of Kaplan-Meier, right? So we know that auto plot doesn't work well with more than one covariate. So we can use GGobserved plot. Right. So now at the same time we know that it is harder to add more covariates in the model. For example, we cannot add numerical data here. We can, but it will be messy. Okay, I can show it. Can show you. Let's say we put this as some age, right? Karnoff. Okay, Karnoff. Pattern, which is just the variable Karnoff. Okay, Karnoff. And let's see, we put this as model number 2. We don't want to run this. You see, it's very messy, So it is not useful at all for numerical data in Kaplan-Meier. So don't do Kaplan-Meier if you got numerical data covariates. So instead we use Cox. So for this model we use the function Cox pH. Okay, Cox pH, and the covariates are treatment, cell type, Karnoff score, diagnosis time, age, and prior treatment. And data is the veteran data. Then we run the summary Cox to get these results. So this is the log hazards. Okay, it means that for treatment 2, and the log hazard is 0.294 compared to treatment 1. For small cell CA, the log hazard is 0.861 compared to the baseline, the reference group, which is what? The reference group of the tumor, which is squamous or large. Squamous or large? Squamous. Squamous. Okay, squamous compared to squamous. Small cell has the log hazard of 0.86. Why I said 0.86? Because this is minus 0.01. So it means that 2.946 times 10 to the power of minus 1. So you have to move the digits to the front one step. Okay. So this is the exponentiation of this. So this is the hazard ratio. Okay, this is the hazard ratio. So so those on treatment 2, there is 34% higher risk of something. Okay, of something. I'm not sure what is the outcome of this one, but of the event compared to treatment 1. However, the p-value is not significant. Okay. Right, and then we can use the surf-fit function to get the survival probability. Surf-fit, okay, the same like before. Surf-fit of model Cox, and then we can use the autopilot function, and this is the adjusted survival probability for model this one, for model Cox, which has the treatment variable, cell type, Karnofsky time, diagnosis time, age, and prior treatment. So this is the estimated survival probability from that model. Okay. So now we want to check for the proportional hazard assumptions. We run the Cox ZPH function. Which model? The Cox model. This model. Okay, this model. And then we use Kaplan-Meier method, and we choose global equal true, and then we type this back to provide us with the results. The p-value for the global test, the chi-square value is 34.6, very large, and the p-value is 0.00003. So it suggests that there is a violations of proportional hazard assumptions. So the next question is which variable that violate the proportional hazard assumptions. So we look at each of the model, each of the covariate, and we see that there are two variables that have problems with proportional hazard assumption. One is the cell type, and two is the Karnofsky score covariates. Okay. So and you can see this. You can plot this by using the function plot, and you can see for treatment is rather okay, and that's why for treatment the p-value is not significant because it's like flat, so that doesn't violate the proportional hazard assumptions. But for cell type is also alright, but for Karnofsky, you see, it's like like a wave. Okay, like a wave. So from time 8.2 to time 9:54, the hazard looks rather similar. However, from 54 to 130, the hazard looks like it is increasing, and after that it looks like it is decreasing. So the hazard itself is not proportionate over time. It's it's wiggly. Okay, it's wiggly. This is for diagnosis time, and this is for age. This is for prior, and did I miss something? I thought we have two. Cell type. Okay, cell type. All right. Oh, cell type. Yeah, I thought that this looks all right, but from the analysis, it shows that the cell types is also a problem for proportional hazard assumptions. Okay. Okay. In real case scenario, will I consider this as violations of proportional hazard assumption? I don't think so. Okay, I don't think so. I don't think so. I think I will take this as acceptable. I will take this as acceptable. Not so obvious in terms of the non-proportionality itu. It looks like kind of straight, right? Except for this bit lah. Okay, this bit. Compared to Karnofsky score, which is quite obvious. Diagnosis time is okay. Age looks alright, and so on and so forth. So because of that, what can we do next? Since we thought that Karnofsky score is the one that violate the proportional hazard assumption, then we might want to stratify variable Karnofsky. Okay, so what we can do now is to use what we call as the stratified Cox regression. okay, stratified Cox regression, same function Cox pH. Just put a small function here, strata, and which variable you want to stratify, Carnot, okay, Carnot, and then run the model. Let's say we name this model as str.cox2, okay, and then we use the function summary to see the results, and we know that Carnot will no longer be here, okay, because now it is adjusted, okay, it is stratified. So this you will see, you will not see Carnot variable in the model anymore. And I think you can also add cell type. Okay, let's see we do this. Okay, we stratify two variable. Let's stratify two variable. Let's stratify Carnot, and then stratify strata cell types. Okay, cell types. Strata cell type. Okay, let's name this as strcox3. Okay, and then we summarize, type summary to get our the result, str.cox3. Okay. So now we have the log hazard for treatment, diagnosis time, age, and prior. This is the hazard ratio. This is the standard error, and this is the 95% confidence interval for the hazard ratio. But we don't see cell type anymore. We don't see Karnofsky anymore, because we have stratified those two variables to make sure that they are now they are corrected for the proportional hazard assumption problem just now. Okay. So if you think that cell type is important, then if you stratify, unfortunately you will not get the estimate for that lah. Okay. So and in my opinion, judging from this plot, I don't think the cell type is really a big problem for proportional hazard assumption. So I don't think I will stratify this. So I won't. I think I'll take. I just stratify for Karnofsky sahaja. So yeah, that's all. That's all for